now we can look at the enthalpy of a reaction, or the heat of the reaction. So it's the change in enthalpy when you're looking at products and reactants. So products are kind of like your final state, so you're going to do products minus reactants, or final minus initial. So enthalpy is an extensive property. So if you remember, we talked about extensive and intensive, and was that chapter 1? Intensive is independent of how much you have, and extensive does depend on how much you have. So if we had this reaction, let's just look at a simple combustion reaction. So we have methane plus some oxygen, and we get carbon dioxide and water, because that's a combustion reaction, 2H2O. Suppose the delta H here, the enthalpy of this reaction, it's exothermic because it's combustion. So suppose it was 890, I don't know why that happens, kilojoules. This is for 1 mole of methane. This is for 1 mole of methane. If I had 2 moles of methane, suppose I had 2 moles of methane, I multiplied everything here by 2 instead. So this is for 1 mole of methane, right? For what? Because this is what I have in here. If I had 2 moles of methane, I would just multiply that by 2. I would say that that's negative 890 times 2. And what do you get when you do that? So you get like 1780 kilojoules. Oops, 80. So it's extensive. It depends on how much you have. And you're going to refer back to the chemical equation in order to get that data. So this is like getting a new conversion factor. So you can go from heat to moles of something, and then suppose they didn't give me moles. What if they gave me grams? I can go from grams to moles, and then compare moles of methane to kilojoules, and then I can figure out how many kilojoules I would get from that. So this enthalpy is an extensive property, depends on how much you have. Delta H for a reaction in the forward direction is equal in size but opposite in sign. This is just saying that if it's endothermic in one direction, it's exothermic in the other. So let's look at this reaction again. If I flip this around, right, and this is exothermic, right, this is exo. If I flip this reaction around, I made the products reactants and the reactants products. So carbon dioxide and water were products over there. Now, if I flip this reaction around, keeping everything the same, just reversing the positions of the reactants and products, I know what the enthalpy will be in this case, because if it's negative 890 kilojoules in that direction, it's going to be positive 890 kilojoules in this direction. Oops, kilojoules. And the last piece that it's saying is just the delta H for the reaction depends on the state of the products and reactants. So when you're looking these up in a table, when you're trying to figure out what the delta H is for a reaction, you're going to look this up in a table, and you want to make sure that you're looking up, if this is a gas, that you'll look up carbon dioxide gas instead of liquid. So the phase of matter will determine the delta H of the reaction. So that'll change depending on what the phase of matter is. Alright, so let's try to do a stoichiometry problem involving enthalpy. So here, just to interpret this equation for a second, this says 2 moles of hydrogen peroxide are going to decompose into 2 moles of water and 1 mole of oxygen. And that process is going to release negative 100, so negative means it's releasing. This is exothermic. It's releasing 196 kilojoules. So calculate the quantity of heat released when 5 grams of hydrogen peroxide decompose at constant pressure. Well, I know that for every 2 moles, I get this much heat. So how much would I get for 5 grams? I have no idea. I need to convert from grams to moles. How do I go from grams to moles? Molar mass. Good. So I'm going to take the grams of hydrogen peroxide. That's H2O2. I'm going to calculate the molar mass. So that's 2 times hydrogen plus 2 times oxygen. That's about 34 grams. 34 grams of hydrogen peroxide. H2O2 for every 1 mole of H2O2. Alright. And then I'm going to look in this chemical equation here, and I see that for every 2 moles of hydrogen peroxide, I get negative 196 kilojoules. So for 2 moles of hydrogen peroxide, I get negative 196 kilojoules. And so when you work all that out, so just multiply all those things through, you get negative 14.4 kilojoules. Okay. so that's how much I would get for 5 grams. You have to go from grams to moles using molar mass. You guys remember how to figure out molar mass. And then moles to kilojoules using this chemical equation. So if you're just pulling out the stoichiometry, the stoichiometric coefficient, and that number there. Now, can we work backwards? What if they tell us the heat and we want to figure out how many grams, and maybe not of grams of a reactant, maybe grams of a product. So if negative 502 kilojoules of heat is released, how many grams of oxygen were formed? So I can go back to this equation. I can say for every 2 moles of hydrogen peroxide, I get 196 kilojoules released. 2 moles of water, 1 mole of oxygen. So I'm really going to look at this 1 mole of oxygen and relate that to my heat in this problem. I'm going to start with heat because that's the only thing that I have. It's the only number that they give me. So I'm starting off with negative 502 kilojoules, and I basically want to convert heat to grams. Well, I can't go right from heat to grams, but I know that for every negative 196 kilojoules, that's equal to 1 mole of oxygen. And then I know that now I have moles of oxygen, but I'm looking for grams. How do I go between moles and grams? Molar mass. For every 1 mole of oxygen, I have 32 grams. Oops. 32 grams of oxygen. So you're going to work that out. So I got like 81.95 grams. 81.95 grams. And I'm going to convert that to 3 sig figs, so I have like 82.0 grams of oxygen. Whoa. That was 82.0 grams of oxygen.